Hi class, Dr. Bevilacqua here, doing a screencast on scale height. Let's begin with a sketch of the Earth, and we have the atmosphere above it, and we consider a tall, thin column who has an area A and a small change in height dz, and the volume of this little element dv equals A times dz. Here's the z-axis, which is pointing upward. The force due to gravity is downward, and because it's in the opposite direction of z, it gets a minus sign. M is constant, so a change in force, dF, is equal to minus the constant g times dm, the change in mass. Next, we consider pressure, which we know is equal to force per area. In this case, it's minus F because of the minus sign that we just considered over here. Then the change in pressure as we go upward is equal to minus dF, the change in the force, divided by A, which does not change because it's constant. We can then go in and replace our value of dF with the value that we derived up here as minus g dm, and we're left with this expression shown here. We can then, over on the side, write down the definition of density as mass per volume, but because density is an intensive variable, it doesn't depend on the amount of material. A small m dm divided by a small v dv gives the same value of density. We can then solve this for dm and substitute into the equation on the left. And when we do that, we replace dm with rho dv, and we're left with minus g rho dv divided by A. We can go ahead now and carry this final equation over onto the next page. And when we look at this, we can see dv over A. We can go ahead and replace dv with the definition from our sketch, in which dv equals A times dz. When we do that, we end up with minus g rho A dz over A, and we can go through and cancel the A's to leave us with dp equals minus g rho dz. We can then write down the definition of density from the ideal gas equation as density equals mass per volume, which is equal to pressure molecular weight over RT. We can see that when we substitute this in, this is going to bring pressure into the equation, and we're going to be able to take that over on the left side with the dp and go ahead and do our calculus and integrate. So let's go ahead and substitute rho with p molecular weight over RT. And we're left with this expression where I've grouped the terms for rho inside of the parentheses. We can then go ahead and take the pressure and bring it over onto the left-hand side of the equation. We're left with this expression here, in which we can now integrate the left-hand side. These four terms are essentially constant with respect to distance. Temperature varies slightly, but we'll neglect it in this simple derivation. If we take these four constants and invert them, we have this expression, and this is equal to the scale height. We can then do a unit analysis. We take R in terms of joules per mole Kelvin, temperature Kelvin, acceleration due to gravity as meters per second squared, and molecular weight here is kilograms per mole to be in SI units. We can then go in and we can look at the definition of joules. We know that that's units of work. That is force times distance, or mass times acceleration times distance. Mass is kilograms, acceleration meters per second squared, distance meters. And then we can go through and we can cancel. And I've color-coded that here. And if you look at that, take a minute, maybe pause the screencast, you can see that ultimately that this whole expression comes out in units of meters, just like we would expect for scale height. We can then go ahead and substitute the value for h naught into this expression, and that gives us this more simplified version. We can carry this over then onto the next page, and we can go ahead and do our integration. And when we do that, we integrate on the left-hand side, starting with the surface of Earth, where z is 0. The pressure is the atmospheric pressure, P naught. And at any distance z above the surface of the Earth, the pressure is P. The integral of dp over p is the natural log of p. We pull minus 1 over h naught as a constant out in front of the integral on the right. We integrate the integral of dz as z. We evaluate these. On the left, we get the natural log of p minus the natural log of p naught. Ultimately, we can simplify to this expression. On the right, we simply have z minus 0, or z. We can then go ahead and raise each side to the exponent of e, and this simply e to the natural log of p over p naught reduces to p over p naught, and on the left-hand side, we end up with this expression. We can bring the p naught over on the right side of the equation. We can then graph this equation, and you can convince yourself that it looks like this. It's an exponential decay. When z is 0, we end up with e to the 0, which is 1. So at z equals 0, the pressure is p naught. When z is equal to h naught, we get e to the minus 1, or p equals p naught over e. And I've plotted those 2 points here. And so we can see that what happens is that as we move above the surface of the Earth, the pressure decreases, and that's because the molecules thin out. Let's go ahead now and look at the value of h naught. We use the expression that we wrote down on the previous page as RT over G, molecular weight. We substitute in the appropriate values. Just a couple comments. One is that the temperature we're assuming here is about 298 Kelvin, or room temperature. Of course, that varies slightly, as I mentioned, but it's a good approximation. And the other is that the molecular weight of the atmosphere is the weighted average of nitrogen and oxygen, weighted for their abundance. Since the atmosphere is mostly nitrogen, this mass is close to that of N2, but slightly more because of the contribution of oxygen. When we plug these into our calculator, we end up with an answer of 8,800 meters for the scale height. If we convert that into miles, this is about 5.5 miles. It's useful to visualize this as well. I've made a little sketch here of the Earth. The radius of the Earth is 4,000 miles. The thickness of the atmosphere ultimately is about 10 times, we can approximate it as 10 times the scale height. Of course, it's thinning out. So you can see that the atmosphere is just a thin skin over the surface of the Earth. It's even exaggerated in this drawing. And then lastly, the other thing that we can do to visualize this is that because the pressure decreases as we move above the surface of the Earth, then the column thins out. And I've sketched this here as a thinning out column of air. Thanks for listening.